Okay.
Welcome everybody to the Georgia Tech Graph Theory Seminar. Our speaker today is Florian Pfender from University of Colorado, Denver, and he will tell us about inducibility of graphs and tournaments.
Yeah, hello everyone. Thanks for joining us. And yeah, I'm going to give this virtual talk today. It's of course not quite as nice as being there in person. On the other hand, I saved myself a plane trip. So yeah, this talk is about what we've been doing for quite some time, Bernard and I. We are using flag algebra methods of Razborov to talk about things like inducibility, meaning counting subgraphs, classical extremal graph theory, counting subgraphs in graphs, and directed graphs, tournaments, all kinds of structures. So all of this is joined with Bernard. Some of it is joined with one of my students, Conor Mattis, and some of it is joined with another one of my students, Michael Phillips. And yes, if you've seen someone introduce flag algebras to you in the last few years, you may have seen some of these slides before. There's a whole funny history about it that like I made some slides for my job talk 9 years ago, and then they took a tour around the world, and I've heard of people that I've never met using some of my slides, and then Bernard edited some and improved and back and forth. And so they pop up everywhere nowadays, but it's kind of fun. So I talked to Anton and he said like not every one of you guys has seen much flag algebra. So I'm going to give like a little intro on what this is all about. So I'm going to start a little bit with an intro on flag algebras, which is going to take anywhere between 10 and 15 minutes. And then with an example in it, in the end, one of our favorite theorems, Montel's theorem, proving it with flag algebras. And then we're going to go to a couple applications for these flag algebras, and these appear in the title. One is the induced subgraphs, where we're talking about fractalizers, fractal structures in graphs, and the other one is talking about tournaments. So let's see where we're going. Flag algebras, as I said, first introduced by Razborov in the early 2000s, published in 2007, and when he did that, a lot of people jumped on it, and his methods are very powerful in the sense that a lot of things where people before had to think real hard and use a lot of ingenuity, nowadays you can do certain things with the help of a computer with less ingenuity, which of course you could be super sad about this, because before you needed all these people being geniuses to do this, and now we do it with the click of a button on sometimes a very large supercomputer, so we're more powerful. But on the other hand, what really happened is just that the work has shifted. The stuff that can be done by a computer is now done by a computer, and the stuff where we still need the human brain to be smart is done by human brains. So we just have found part of what we had to do before, found out that that wasn't all that important, that a person would do it, and we just shifted to another part, and we can be much more powerful and proving lots more things with this. So the original design is to attack extremal problems. His paper was formulated in talking about what was it? More formal languages, formal model theory. Lots of graph theorists, extremal people couldn't even read it because they didn't have the right background. I was fortunate to sit in an office with someone who actually had that background to explain it to me at the time. And in general, we will focus on it though on the topics of graphs here. In general, it works very well if we can formulate our problem in terms of small subgraphs, and the structures we're seeing also are sort of determined by very small substructures. So say a blow-up of a small graph as an extremal structure is something that flag algebras can often see. If our structure is much, much more complicated, flag algebras have a problem. So if you've heard about graph limits. If your limit, your graphon, looks fairly simple, meaning is a step graphon with fairly few steps, flag algebras work really well. They can even see the grays in these graphons. They don't just see black and white. But once it gets very complicated, these flag algebras have trouble. And this last line that I wrote there is everything that flag algebras do, or not everything, but yeah, typically everything that they do is talking about very large graphs or graph limits. And so all our results are like, if n is large enough, then this and this is true. And when I say all our results, I'm lying because you can do tricks to pull this back, but so far so good. So, oops, yeah, we're gonna, as I said, we're gonna use an example problem to show this method. It's Montel's problem that you've all seen before, that if you don't want any triangles, you can only have half the edges. And this is, well, I don't have to say this in the seminar, it's a typical problem of extremal graph theory, where you want to maximize one parameter or keeping some property. And you get a threshold behavior, and then once you find that bound, you're also interested in what the extremal objects look like. What do these objects look like that have the most number of edges in this case? And to introduce the flag algebra notation, I'm going to want to talk about graphs. So we have edges and non-edges, and because non-edges just don't show up so well on a white background, I'm going to color them in blue. So, and here are my symbols, the players. Something like this will stand for, one could say, the density of triangles. So in other words, if I pick 3 vertices at random, the probability that I see a triangle, a red triangle in this case. This one, same thing. If I pick 3 vertices at random, the probability that 2 of them are blue and 1 of them is red of these edges. I don't care about labels here in this case. Labels come in at a second step, at a different step. I can also talk not just about graphs in general, but I could have like a root of a graph. I could have like 1 or 7 vertices or something like that be labeled, and they're fixed, and the graph in between them is fixed, and all the others are just the ones that I pick randomly. So in this case, I get a picture like that, and I use these yellow boxes to denote those. And quick question, if I am in a graph, I can do algebra with these objects. So what's the answer on that? So a red edge plus a blue edge.
1.
1, right? Yes, exactly, right? Because any edge is either red or blue. So the probability that I see a red edge plus the probability that I see a blue edge, if I pick 2 vertices at random, is exactly 1. And so this is sort of a very basic identity that I'm going to use. These guys, again, are called flags, usually, and the type is whatever is induced by these yellow vertices of a flag. And you can only really do algebra with flags of the same type, and then there's going to be a way to get rid of these labels at some point. So again, we have other identities like this one, which is the same one as the one before, just on 3 vertices, right? All different kinds of color combinations we have. We can switch between different sizes of subgraphs. You see this, right? If you want to look at the probability that you see a red edge, if you pick 2 vertices, you could pick 3 vertices and throw 1 away. And if you pick 3 vertices, you have one of those 4 outcomes. And if you throw 1 away, your probability that you find a red edge is different depending on what you saw first. In the first case, you always see a red edge. In the second case, you have a 2 out of 3 chance, and so on and so on. So you get an identity like that. Down there is just the probability, conditional probability version of that. You can multiply. It's an algebra. So especially if you have a root, it's something that's very similar to what's called a gluing algebra. So if I, for instance, look at these 2 flags on the left side, which both stand for the probability that I pick an extra edge, extra vertex that I see a red edge. Well, what happens if I pick two extra vertices, the probability that both times I see a red edge is essentially the probability that I first see a red edge and then a red edge the second time. There's a little O of 1 in here because, of course, this excludes the case that I picked the same vertex twice, but everything is in the limit, so we'll just forget about the little O's in the end. So like I write them here on this slide and never after. And what's this question mark here? Well, for this left side, I don't care if the connection between the edge between the two extra vertices is red or blue, so I just write it out like that. And of course, yeah, okay, this is this. And then if I multiply two of different colors, I have to be a little bit more careful because the symbol that I have right here counts both if I first see the red and then the blue, where the multiplication, I'm saying the first one needs to be red, the second needs to be blue, so therefore we get the 1/2 here. And these are the kinds of identities we're talking about multiplication, and you can expand all this to much bigger flags too, and everything works out. And now the one thing that I said earlier, we can get rid of these labels by averaging out. This is what's called the averaging operator. And so I can just push my root around in my graph to every vertex and average all these values out over the whole graph. And then this right side is essentially the average of the densities that if I first pick the root, that the other two vertices make this triangle. And this left side is just the triangle. And the 1/3 is that I then pick the correct root to find the same picture over here. So again, nothing super surprising if you have a little bit of probabilistic intuition or so. This comes out right away. Some of these slates Bernard worked on, and he always likes the counting better than the probability. I'm more the probability person between the two of us. My intuition is in the first line. Bernard's intuition is in the second line, where this left side just counts all structures of this type, because there's n-choose 3 different ways to picking these vertices. And the right side also counts out all these structures because you can push your root around the whole graph. And once you've picked that, then you have n-1 choose 2 vertices to pick around here. And this corresponds to everything up there because, of course, n choose 2, n-1 choose 2, and the limit is the same. That's the little O of 1 again. So for the all red triangle, you don't have the 1/3 because there you can get the root wherever you want and account like that again. So these are all the identities that we've seen before. We want to speed through a little bit. I promised you I'd be done in 15 minutes with this part, so I better speed through it. And let's see how we can prove Montel's theorem with this language. So we're assuming we don't have red triangles, and we want to conclude that the density of red edges is at most 1/2. Of course, this is not quite Montel's theorem because everything is up to little o's, but well, good enough for us. So we start with an inequality, which is certainly true because a square of some number is always greater or equal than 0. And now what do we do with this? The right side, we just throw the algebra out and expand it. And let me see my whole slide. And we get something like that by just expanding this with our rule down here. Okay. And now we want to argue about triangles and edges without the root. So we want to get rid of the root there. So we're averaging out everything like this and use our averaging rule to just do that, right? And then we get this line as an answer. Now, this last part, the red triangle, doesn't appear because we know it's 0, so we might as well forget about it. Oops, I forgot what I wrote here. Yep, forget about it now. And we also want to make sure that these edges come in. So we can replace some of these with this identity down here. And we use this identity to write it like that. And so therefore we subtract this once from here and or add this actually once to this because that's 0, and we get this end result here. Okay, so far so good. All of this is more or less just notation. There's nothing crazy that happened. And now realize that any of these flags is always greater or equal than 0 because they're densities. So if we let something with a negative coefficient disappear, then we can only make it bigger. And we have this. So in the end, if you look at this inequality, we have that 0 less or equal than 1 minus 2 times the red edge. So the other way around, the red edge is at most 1/2. So this is the whole proof of Montel's theorem written with this flag algebra notation. It's not easier than the original proof that you may all know, but it's just to get our feet wet with this notation. So what else can we see from this? We can actually see the extremal example in Montel's theorem. We can see the complete bipartite graph. How can we see that? Well, look at this last equation here, this last inequality again. The only way we have equality here is if this last term here is 0, this last probability, because if it's bigger, then we cannot have equality up there. So therefore, we know it's actually 0, and only these two graphs appear on 3 vertices. If we know that only these two graphs appear, we can build up our extremal example by starting with an edge. Of course, we have edges because our edge density is 1/2. And then if we have another edge or another vertex, then it has to look like that. And we put the blue edge, the blue partners on the left side. If we have another one, like we build up a whole blue blob on the left side, and on the right side, we might build up a blue blob. And then we can see that the remaining edges between the two sides also have to be red, because otherwise we would have a blue-blue-red triangle. So they also have to be red, and this builds up our whole structure. So by knowing that certain triangles do not appear from our flag algebra computation, we know a lot about the structure of what we have. We don't know that this bipartite graph is balanced, but of course, this is just basic undergrad analysis that tells us that balanced is the best for a number of red edges. So looking back to this proof here, we started with this inequality, this square, and that came a little bit from nowhere. So I said we can use the computer to do the work for us, but how should we ever use the computer if the computer doesn't know which inequalities to start with? And this is what this next slide is about. So how do we guess that this is the right thing to start for our problem? Well, we have this inequality, this identity always, and we have something like this. We can start with a more generic positive term. If we take a positive semidefinite matrix, this A, B, C, C there in the middle, and multiply it from left and right by the same vector, we know it's always greater or equal than 0. Our choice is now what vector to use here. And there, what we actually do in practice is we just write out all the flags of a given size that multiply to a given size. And the more detail we want, the more computation power we have, the bigger flags we use there, and the bigger the matrices in the middle become. If we multiply this out like before, we get something like this, some constants in front of all these terms. C4, of course, because we don't have red triangles, we can just neglect. And then once we do that, we can add these two things together, the term for the single edge and this inequality, 0 equal, less or equal than something. And we get that this red edge is less or equal than something with these triangles on the right side, depending on this A, B, and C. And now we know that these three guys on the right side together give us 1. So if we increase all the constant in front of these guys to the maximum of the 3 terms, here are our 3 terms, and if we increase everyone to the maximum, then this is certainly true. And so now we can play with our positive semidefinite matrix that informs us what these constants are to make this maximum of these 3 guys minimal. And this is something we can formulate as a semidefinite program, and that even if it's very big, even if it's 1,000 by 1,000 or 10,000 by 10,000 size matrix, a computer can solve a semidefinite program like that for us in reasonable time. And that's, in a nutshell, how this method works. So if we want to find a bound like this one here in the end, we set up this program, which is pretty much automatic if we give it a few inputs, and have a computer run and find the best semidefinite matrix to use here to give us the best possible bound that we have. So this is now the part that we don't put much brain in anymore, and now we just use it. Of course, technically, we still have to round everything and to get proper proofs, but this can all be done.
A quick question, just to clarify, in this vector that we're multiplying by the semidefinite matrix in the middle, do we use flags of the same type?
Yes.
They all have to be the same type, right?
We would use flags of the same type, but we go through all the possible types you could possibly have, and essentially have either several semidefinite matrices or sort of like a big semidefinite matrix with a block structure, whatever you want to call it, right? Same thing. But we do that. We just specify the size of the type. We specify the size of the, actually, we just specify the size of the graphs that we want to have in the end and have the computer go through all possible types into anything. If we hit the thresholds where we run out of computing power, we might just use specific types we like better. But usually you don't even think about it. Usually you just let them run everything.
Thanks.
And so this was the little intro. I hope. Yeah, I don't have time here, so I don't know where I'm running. There it is. Okay, I guess a little bit longer than I thought, but that was how this flag algebra method works. And now let's get to the applications for that, or for applications that we are interested in more recently. So we're talking about fractalizers now. And what are fractalizers? So let's take a triangle to start with, and let's replace every vertex by a graph or an independent set, say. So this is just a blow up of a triangle here. And well, instead of replacing it by an independent set, we could replace it by itself again and get this structure, which is sort of a fractal structure that goes deeper and deeper and deeper in there. Chose a triangle here to draw this, even though, of course, a triangle, this fractalizer of a triangle is not all that interesting because it just becomes the complete graph if I do that. But if I were to do something bigger, the picture would become confusing. So I'm just going with this right now. And if you look at it, why is it called a fractalizer or a fractal, say? A fractal graph? Because, well, if I zoom in one place, I don't know if this is working right now. It didn't work. Oh, now it works. If I zoom in one place, it looks the same again, right? So here we are. Oh yeah, now it's actually, the movie's actually playing. I should have run through this before. Okay. These are the nice pictures that Bernard sometimes makes, where Gil Kalai comes up to him and asks him if he can do it for him in his talks. So even though they're about completely different things, but it's always nice to have someone who has some TICS skills with you, but yeah. Okay, so now the question is, what kind of results do we have that have iterated structures like that? I told you earlier that flag algebra is good seeing simple blowups of small graphs. Flag algebra is not as good at seeing these guys. So if we want to maximize something that has this fractal structure in the extremal example, flag algebra can't quite see it. It's usually off by a little bit. And then you have to use other methods to finish the job. Nevertheless, for like indirected graphs, Razborov and Vaughan found that these outstars with 2, 3, or 4 out edges are maximized by this fractal-like structure, where you're repeating over and over this iterated construction, where one side is this time it's empty and the other side is just repeated what you had before. And they used flag algebra for this and proved it. And this time, flag algebra actually gave the sharp result because the structure apparently is small enough to be seen. This was improved by Howe, your neighbor, that this is actually true for all outstars. And if something's true for all size kind of subgraphs, it's usually not the plain flag algebra method that does that. He did this by hand. He saw some inequality in there that he proved that would do the whole job. So, and the existence of this inequality is probably the reason that Razborov and Vaughan could see this with flag algebra, because this inequality that Huang proved was small enough that flag algebra could see it without telling them that that's the inequality that's at work here. So that's another story. Sometimes flag algebra tells you something, and if you dive deep into what it tells you, and maybe you can understand it, maybe understand the language, you might be able to use that and prove something more general. Howe didn't dive into flag algebra. He just did it the old-fashioned way. Here's another very old result, or not very old, of course. Another result that looks like that. Latgir, Kral, and Norin showed that this 3-vertex path on directed vertices also has a fractal-like extremal structure. As far as I know, they never wrote it up or never published it. But we can also prove this, so we know it's true. And Piccolco actually showed that this is not uncommon. So these fractal-like structures are very, very common as extremal graphs, maximizing the number of induced copies of of another subgraph or of a family of a subgraph. And we first encountered this when we looked at an old problem by Erdős, where it was a 3-colored graph now, not 2-colored, so not a normal graph, but like we now have 3-colored complete graphs. And we want to maximize the number of rainbow triangles in this in a KN. And this might be your first guess. You just take that rainbow triangle and take the iterated blow up of itself. Turns out is not as good as if you start with a 3-colored K4 and blow up this instead. And we actually proved that this is best possible. So Erdős and Schosch was the conjecture. They already knew of this example, and we proved it with the help of flag algebra that this is best possible. Again, it's not a straight up flag algebra computation. We used some tricks that I'm going to show you in a different example in a little bit. The flag algebra itself doesn't quite give you the right bound. It gives you the 0.4 is the right bound. Flag algebra gives you 0.40006. So you needed something else. For the definition, now we talked about these fractal-like structures. In a few years ago, Fox, Wang, and Lee defined what a fractalizer actually is. So they took this word and named something. So, and they say a fractalizer is a graph that essentially is it's a blueprint to maximize the number of copies in itself if you just iteratively blow it up yourself. And they say you want to call it a fractalizer only if this goes through the lowest level. So all the way down to 1 vertex, this iterated blow up over and over and over again. So at first you would think, well, with flag algebra, you can't prove that because you can't prove for the small stuff, but it is possible in the end. And they showed in their paper that actually almost every graph is a fractalizer. So if you take a random graph on enough vertices, it will almost surely be a fractalizer. And they show this by showing that certain properties that random graphs have are sufficient to show that a graph is a fractalizer. But they didn't know of any fractalizers. They knew almost all graphs are fractalizers, but they didn't know of any. Other than, of course, the trivial ones, the complete graph and the empty graph. They're, of course, fractalizers because maximizing the number of complete graphs, you just take a complete graph, and that's the fractalizer of the complete graph, or the fractal of the complete graph. But they didn't know of any others. And we had this, this nice little picture of some people looking hay in a haystack. This is what this job is. And there's another history of this, is that Bipartite and Golombek, when they talked about inducibilities, they didn't have the word fractalizer, but they conjectured that all cycles except the 4 cycle, which has a different structure, are fractalizers or fractalizer-like. So they didn't claim that they were quite as good as Fox, Wang, and Lee asked. They didn't claim that you needed to go all the way through the bottom level of few vertices. They just say in the limit, the density is maximized if you take the fractal of a graph. And this is one of the more famous conjectures in this field of inducibility. And we've worked quite a bit on this. And we showed that C5 satisfies this conjecture. Oops, what happened here? Oh, I made a mistake in my write-up. Okay. So the second part actually is new. And that's not even, the second part is new. We proved that C5 is an asymptotic fractalizer. We proved that C6 and C7 are asymptotic fractalizers in this sense. And we also proved that in the directed version, C4 is already an asymptotic fractalizer. And recently, we actually proved that C5 is better than just an asymptotic fractalizer. C5 essentially is a fractalizer. The directed C5 is a fractalizer, and C5 is almost a fractalizer in the sense that, let's see. Oh yeah, here, this is the result I want to talk about. C5 is a fractalizer. No, it's almost a fractalizer. The reason that on 8 vertices, there's one example. So on 8 vertices, there's an example that has as many C5s as the blow-up of a C5, but it's not a blow-up of C5, which then means that even for bigger numbers, whenever you come down and one of your parts has 8 vertices, you could replace the blow-up of a C5 over here by this Möbius letter over here, and keep the same number of 5 cycles. So in that sense, it's like as close as you can be to a fractalizer without being one. There's one little counterexample. And I don't have much time, I guess. It's 10:21, well, a little bit. I can run you through a little bit of an idea of how we proved the original result and then what we do now. And what
you have at least 20 minutes.
Okay, 20 minutes, good. Yeah, but I want to talk about a different topic too.
Right, yeah, I'm just checking that here.
Okay, great. So I'll look at that. So here's the sketch of the proof, what we want to do, right? So our goal is to show this fractal structure of the C5 over here, that we have that. And what we're going to do is essentially prove that the outside C5 structure is there, that it's a blow-up of a C5, and then use induction to go to the smaller ones. And so our goal is that whenever we maximize the number of C5s, we have a blow-up of a C5 as this outer layer, without talking about the insides of these blow-up graphs. So what do? We just pick some induced C5. We partition the remaining vertices in 5 classes, depending on what they look like. So we have these 5 classes. And we say that we prove that almost all edges are correct, meaning edges are where they are, where they're supposed to be, and non-edges are where they're supposed to be between these parts. And then we use some stability results to show that actually everything is correct. And then we balance the size of the parts. So this was the very quick and dirty thing. Let's see a little bit more detail on this. So that was the very short movie. Let's do a little bit more detail. So we pick not just any old C5, we take a good enough C5. What's good enough? We take a typical C5. We take an average C5, in fact, average by some sort of measure. And flag algebra tells us what this C5 has in measure, this average one. So again, we partition the remaining vertices in 5 classes like that. And by determining where they fit best in each of these classes. Oops, where am I going? Flag algebra again tells us that almost all the edges are where they're supposed to be between these parts. So the edges that are supposed to be there are there. The edges that are not supposed to be there are not. How do we do this with flag algebras? We're looking at these 7 vertex subgraphs and looking at the densities of those. And essentially we're saying the 7 vertex subgraphs that look like this with an edge missing are very rare. And the 7 vertex subgraphs going across where we have 2 and 2 with an extra edge here are also very rare. And we mostly have, and we have a lot of these. And this will essentially tell us that almost all edges are there, where they are, where they're supposed to be. So this is the other one. And then we use stability arguments, which is more classical extremal graph theory, saying that, well, if we're almost there, making an incorrect edge correct, meaning taking away an edge that shouldn't be there or adding an edge that should be there, can only increase the number of 5 cycles in our structure. These kind of arguments we're making, or maybe sometimes we're making bigger arguments where we're not just replacing one edge, but like a whole set of edges. And that tells us that all the edges are there. And that is essentially the end of the proof. The original proof actually had a little bit more. We didn't have the 5 parts, but we had a little trash set that we had to get rid of. But by now, after analyzing this proof more and more, we can actually, the better proof is to never have extra vertices, to have partition everything to start with. And we can do that. And then in the end, well, again, the typical argument balances the size. So that's the proof. What kind of flag algebra calculations are we doing? So we tell flag algebra, or we tell our semidefinite program, that the C5 density is where it's supposed to be. 1/26 is exactly the density in the extremal graph, or the conjectured extremal graph in this fractal. And then flag algebra tells us that the density of these 2 guys, these 2 7 vertex graphs, is at least this, which is big, which is very close to actually the density in our extremal graph. So it's very good. Like we're just off in the 5th digit or something like that. So if we now fix an average C5, meaning a C5 that if you add 2 vertices to it, in at least an average case, we get that many. We get this inequality up there. Then an average C5, the probability that I add, if I add 2 vertices to it, that I see one of these 2 guys is at least 0.8, something like that. And that's what we take as our C5 that has that. Oops, yeah. And these are so these are the 2 ingredients that we need, that flag algebra computes for us, and then we run with that. Like essentially, because if we have these 2, that tells us that we can partition almost everything, and then we can take a best partition to 5 sets, and then with stability arguments we bring it all the way. It takes 10 pages to do it, but it's not terrible. So now what's new? new is that we can not just do this in the limit. We cannot just do this for very large graphs. We can now do this for small graphs too. So for small graphs, flag algebra shouldn't work. So what do we do with small graphs? We make them into big graphs. We make them into large graphs by blowing up every vertex. And we could do it this way. We can just blow it up into independent sets and now have a graph limit. But to get a little bit of extra leverage out of this, we actually don't blow it up with empty sets, but we blow it up with this fractal. So we get a few more C5s out of this and get a little bit sharper bounce because of that. And then we find out inequalities about these guys. And what we do is that we find inequalities like this one. What we are interested in before is now bounded by some linear function in the number of C5s. Of course, these blowups have fewer C5s than our extremal construction for very large graphs, because they're just not as good, right? They're unbalanced and everything. But we have some control over the C5 density of them, so an inequality like that is good for us. And again, we can do an average argument and get something like that. And the remainder of the proof, we do very much similar stuff that we did before. So if our n is large enough, these bounds are strong enough to bring everything through that we did before. The little mistake that we incur, we can overcome with these stability computations. And for small n, these still give us bounds on how many bad pairs there are, meaning an edge where there shouldn't be, or a non-edge where there should be an edge. And we can essentially look at all of them separately. And like this is, I think when I wrote this slide, this is like, by now it actually is even better than this. We don't have to go to 200. We can do it better like this. Okay, good. So that was like the quick run through of this one. And now I come to, are there any questions? I'm a little fast, I think. I'm talking too fast.
Well, why is C4 not a fractalizer?
Who?
C4.
C4, because you can take the complete bipartite graph balanced.
Okay.
Which has more C4s than the fractal of C4.
Okay, good.
Right? So yeah, that's why C4 falls out of it. And the thing is here, like the other part of this theorem that I quoted about the directed C5 falls out of this too, because for the directed C5, this Möbius ladder is not a counterexample, right? We cannot direct this 8 cycle of the diagonals in a way that all the 5 cycles that we see are directed.
So is the conjecture that all directed cycles are fractalizers?
Yes. Yes, I would say so. Like it's not Pippinger's or Golombic's conjecture, but we believe that that is true. And yeah, and that we actually think that for the undirected cycles, it probably starts with C6. At least we're not aware of a small counterexample for C6 where it's not the fractalizer. We know it's asymptotically true for C6. We think it's true for all C6, but at least so far, we haven't tried too hard, but so far we haven't pushed our methods to it for C6. The nice thing about C5 is that it's self-complementary. So a lot of these computations get smaller because you can sort of, you can apply some sort of symmetry there, and you have to compute on fewer variables and everything. And that means that the bounds typically get better. So I don't know if we could push the same thing through for 6 or that we did here.
If I may ask one more question, since you said about C6, so you proved that C6 is an asymptotic fractalizer. Does it also like here reduces proving that it's a fractalizer to some kind of explicitly bounded finite check, just very big? Like you have to check for n at most.
Like that's what I'm saying. The asymptotic fractalizer is the first part of the proof. So this is just here. This finite check down here is just
I see.
all the way down. Right? For C6, we haven't tried that.
Okay, I see.
I don't like for C6. Certainly for C6, the proof would, like a similar proof would give something like for n bigger than 100,000,
Mhm.
you can do it.
Yeah.
I don't
Okay.
know if it pushes down to 1,000 or if it even pushes down to 100. I don't know. That's something that you would need to finish it off.
Mhm.
We haven't tried.
Mhm.
Okay. So, and now we're going to look at something else. So far we talked about graphs. Again, graphs, you have edges or non-edges. And often there's parallels between graphs and tournaments, because in tournaments, for every pair of vertices, you have a choice which direction the edge goes. So you also have two choices. So in that sense, tournaments are like the same size as graphs computationally. And that's also one reason they're attractive for flag algebra computations, because you can still compute on reasonably large structures. So up to like 9 vertices or so you can compute. If you're talking about directed graphs, like before, like you cannot go up to that many. Like the structure size you can compute on is 6 or 7, depending on your other conditions. So flag algebra can see even less. When we talked about directed C5s, we didn't compute with directed C5s. We computed with general C5s. It just turns out that the extremal example, you can direct every edge so that every 5 cycle is directed. So it's a corollary. Like our methods would not work if we tried the whole thing in the universe of directed graphs. The computations would just get too large. But tournaments, we can compute something. And this, I think, not this summer, but one summer ago, we started some computations in an RU with some undergrad students and tried to find extremal graphs for tournaments. And then once we did that, we looked at some which looked interesting, and then we tried to prove something for them. And so let's start with some small tournaments and see if we can maximize the number of these. So the transitive tournament on 3 vertices is maximized by the transitive tournament, which is like the complete graph is maximized by the complete graph. Very obvious, because in the big transitive tournament, if you pick any 3 vertices, you always find a small transitive tournament. The next one, the only other tournament on 3 vertices, is the cycle. And this one is actually pretty cute, but well known, is that if you want to maximize the number of 3 cycles, it's the same as minimizing the number of transitive tournaments. And you can do this, actually the number is the same if your tournament is regular, meaning every vertex has the same out and in degree, being half of the graph. Let's see, let's do this real quick. Hey, come on. Why does it not want to share here? Okay, here we go. The reason for this is just if you want to minimize the transitive tournaments, right? Let's count them. You can just sum up over all vertices. Let's call it T. And then count every triangle by its root. And so you just count up all the vertices, and you have to look at the out degree of the vertex and pick 2 of those out neighbors. And you don't care which direction they're connected. You will always find a transitive tournament like that. And so this exactly counts the number of transitive tournaments on 3 vertices in your graph, this formula. And so minimizing this means you want to make all the out degrees as even as possible, which tells you exactly what you wanted to know. So this is the whole story on on 3 vertex transitive tournaments. Everything like this was known. But how about 4? oops, why is it not? Okay, 4 vertices. We can start with a transitive tournament on 4 vertices. And again, this is maximized by the transitive tournament. Duh, obvious, right? Because it has density 1. There is essentially 2 other or 3 other tournaments on 4 vertices. There's this one, which if you look at it, is a 4 cycle with 2 diagonals. And I don't care which way these diagonals are directed because these are all isomorphic. So from the transitive tournament, you get this by flipping the edge between the first and the last vertex. That is this. For this one, you can run flag algebra, and it tells you something. It actually tells you the density, the maximal density of this. And you can try to prove it that this is true with all the flag algebra stuff, and you would do it the regular way, showing that certain structures don't appear and everything. But there's actually a more direct proof for this. And let me just quickly draw this cyclical tournament that I talked about here. It's just this. You start with a cycle and a directed graph, and you just direct every edge that same way. That's your cyclical tournament. And in this cyclical tournament, you find this structure if and only if these 4 points are distributed, that none of these gaps is longer than 1/2. Right, the shorter gap between these 4 vertices. That's how you get in this structure this tournament. It's kind of cool because it's not a blow up or anything like that. It's a different sort of structure that you don't see often in graphs. So that you see this in tournaments and it looks different from graphs. And at first we tried to prove this with flag algebra, and we could do it, but it was cumbersome and everything. And in the end, Michael saw that you can just prove this by a simple count again, and it's good enough, right? So how do you count this by a simple count? Let's see. You can count the number of triangles, or the density of triangles is equal to 1/4 times the density of you have triangles plus 1 vertex, seeing all 3 like that, because there's 1/4, like one of the 4 vertices you can delete and you keep a triangle like that, plus 1/4, same thing, you have a triangle, and 1 vertex being a sink to that. That's also 1/4 plus 1/2 of what we're wanting, which is this one. Because here, there's 2 vertices that you can delete and keep a triangle. And because of this identity, you can bring all these guys to the other side. Let's do that on the board. Like that. And like that. And the observation is that the cyclical tournament up here contains none of these and of these, and is regular, so it contains the maximum of these guys. So therefore, the cyclical tournament maximizes the tournament that we want, because it both maximizes the density of directed triangles and minimizes the density of these other 2 guys in the picture, and therefore it's extremal. And so that's pretty cute. And of course, you can use this also to then show that it's the unique extremal structure and all that kind of stuff. Okay, so that was nice. And now I want to show you, okay, I have 5 minutes, I guess. Show you the last tournament, and that's the most interesting one. it lets me share. If it ever lets me. Okay, so the last one is these two other 4 vertex tournaments that I just drew. So here is a triangle plus a source. And of course, if you flip all the edges, of course, you get a triangle plus a sink, but these two cases are symmetric. So maximizing one is just like maximizing the other one. You don't maximize both of them at the same time, but if you can maximize one, you know what to do to maximize the other. And this is the structure that you get. And that's what we loved about this. So the structure looks like this. You have a large part, which is about 6/7 of the graph. 6/7 of the graph is quasi-random, which is a bit weird because you wouldn't have expected something like that. And you have a small graph that points completely at this quasi-random part. And then you go back to the small part and repeat the structure and iterate the structure. So this is nice. This is like we were excited about the structure because this is sort of combining different things. It combines iteration with quasi-randomness, which we thought was cool. And intuition behind it goes as follows, right? What do you want, right? You want typically to see your structure up there. You want one part for your source, which is this little part on the right, and the other part for the triangle on the other side. So if you pick 3 vertices from the left that make a triangle and 1 vertex from the right, then you see your structure. And so the best to do that, of course, you want the left side to be something that has many triangles. So you want this to be regular. And then you want the right balance between between the left and the right. So your first guess would be something like put something regular on the left and whatever on the right, and make it like a 3-to-1 ratio. Of course, that's not best possible because there's another way of finding this guy. And in this case, you can find this guy by picking all 4 guys on the left and just get lucky. And the two things together, that the left side is regular and you have the most of the tournament we're looking for on the left side, is actually enough to show that it's quasi-random. And then, so those are in our structure, those are the only 2 ways to get that. 3 on the left, 1 on the right, or all 4 on the left. And because of that, we know we can, this implies that the best possible structure, if we can prove this, is this iteration, because of course we can have all 4 on the right, and then, but then we have to, the right doesn't depend on the left, because the only way to get something in the big one is to take exactly 1 from the right and some from the left. So we don't care what happens there. So we want to do the same thing again on the right, and we get that iterated structure. So in the end, the proof, if I look at this, let me see, can I do this? Yeah, let me see. Right, so the proof is going to be something like this. We want to show that there exists, we want to show that there exists some sort of cut like this, where all edges go one way, which is going to set up this iterated structure, because across a cut, this guy can only go if the source is on one side and the triangle is on the other side. And then we want to force ourselves, not only that we have this cut, but we also want to talk about the sizes of these guys and the inside of the cut. And we want to show that the left side actually has this property that we have many triangles, so it's regular. And of course, then we have many of this guy, as many as possible, which will show that it's quasi-random. So this is what we want to try to prove, and this is how the proof goes. And this part that we're excited about in this is that we're using some tricks in flag algebra which might be going too far in this talk. So we're, instead of looking at global structures, we're localizing this a little bit by using densities and color graphs and things like that, which is kind of cool. But I'm not going to go there right now. If you have more questions, talk to me about it. I can tell you more about it. I think for this setting, this would be saying too much. Okay, so I think I'm done and open for questions.
Thank you very much, Flo. Let's thank the speaker. Are there any questions or comments?
What does it mean to be an asymptotic fractalizer?
It means this thing that, so in this language, you're let's say it like this, the graph that maximizes the number of induced copies of you is this fractal graph in the limit. That's what I mean by asymptotic fractalizer.
Okay.
So we have this iterated blow up of the graph itself.
Okay.
In the limit, right? So if you know the language of graphons, you could easily define that graphon that is the limit. If you just want to talk about very large graphs, if n is sufficiently large, like all the layers up to that and look like that. That's what it means. And everything is balanced, actually exactly balanced, you could even say, up to plus minus 1. You can prove that even though in the limit language, you would not get the plus minus 1, you would only get little o's, but the balancing arguments typically work down to the plus minus 1 in all of this.
Okay.
Are there more questions? Are there any more questions?
I have a question.
Okay.
So you mentioned this result that almost all graphs are fractal, but it's very non-constructive, right?
Right.
So are there any like non-trivial sufficient conditions that show that an infinite family of graphs are fractal, other than the complete graphs?
No, nothing that is better than what Fox, Lee, and what the three have done. A similar result of them was independently proved by Euster. He also shows that almost all graphs are fractalizers. He didn't use the term fractalizer because he didn't know their result. You can't really compare the two results because in some aspects one is stronger than the other, but it feels like the result I cited, like they talk more about structure there. They give fewer conditions and things like conditions are like the graph doesn't have twins, for instance, right? Twins meaning two twins, true twins or not, or untrue twins or false twins, whatever they're called, right? If two vertices have the same neighborhood, they're called twins. If you exclude whatever happens between these two vertices, they're either false twins or real twins, true twins. And it's fairly easy to see that if your graph doesn't have that, or no, if it does have that, it cannot be a fractalizer, because then you can do better by essentially throwing these two guys in the same blob, making that blob either complete or empty, depending if the edge is there between the two or not, and then playing around with the sizes of all the blobs again.
So that is why C4 is not a fractalizer.
Right, C4 cannot be a fractalizer because of that, right? You just throw the opposite vertices in their own blobs, and that's better, right? Like if you look at the complete bipartite graph, it's much more likely than that you pick 2 at random if you do the whole thing than if you would look at this as a blob of a C4 where you want to hit every vertex in the C4 exactly once, right? That's more or less the thought behind it. And random graphs have that property, but of course that property of not having twins is not sufficient, right? Because otherwise I could throw down a whole list of fractalizers because many graphs don't have twins, right? But of course, you can rule out all examples that have, if you're looking for fractalizers, you can rule out all graphs that have twins. They can't be fractalizers. But then they have more complicated conditions that are sufficient for a graph to be a fractalizer. And these more complicated conditions are satisfied by random graphs. That's how they get their result. And they're actually satisfied by much larger graphs, or like much larger classes of graphs than just random graphs. But they're not conditions that you could look at a small graph and see if an if and only if kind of thingy. Like they wouldn't work. So in that sense, like you can't use their result and say this is it, right? Like of course you can use their result and do a random graph on 1,000 vertices, and chances are you find a fractalizer, but you couldn't prove it.
Is it correct to think that some kind of sufficiently quasi-random graphs, like there is an explicit notion of quasi-randomness for which sufficiently quasi-random graphs are fractalized?
Yeah, like yes, like all these things, like the conditions they have are fulfilled by quasi-random graphs. So not just by random graphs, but by quasi-random graphs, and even bigger groups of graphs fulfill these conditions. So their class of graphs that are fractalizers is much bigger than the random graphs. But of course, the random graphs are almost all graphs already. So in that sense, making that class much bigger is a question.
Right.
But we're still hunting, like in a certain way, this directed C5 is the first one someone has proved something like that is an actual true fractalizer. The directed C4, we haven't tried. We might be able to do that, but I don't know. Directed C3 is not a fractalizer. To your question, all directed cycles are fractalizers? No, directed C3 is not a fractalizer, only asymptotically. So there is a small counterexample.
Are there any more questions?
Flo, I have a probably unrelated question. So there's a conjecture of Aldous, Folgery, and Spencer about how many edges you need to remove to make it bipartite. That involves this blow up of C5.
Right.
So I guess flag algebra could be useful here. And
yeah, we've worked on this. We've worked on this with flag algebras and everything. It helps, but and we made some progress on it, but we couldn't push anything through. So we worked on it with Yoshi and Bernard and the people in Illinois, and yeah, that Anton knows pretty well. So we tried, and yeah, that's a pretty famous one, and we couldn't do it. And
so no improvement at all. Like I guess
we couldn't, like on that one. Let me think. I think the best known bounds are by flag algebra now, if I'm not mistaken. Right? Yeah. So we can do something with it. We could not improve on the bounds that other people had gotten with flag algebras before, other than being able to use a bigger computer and compute on one more vertex. So the bound is better, but it's not something you would publish, right? You said like, yeah, I got a big computer, I can compute one more vertex. So therefore my bound is a little bit better than yours without having new ideas. So so we couldn't do more than that. And like on that conjecture, certain things are known, right? Like it's known for certain densities of edges that it's true that the blow up of the C5 is the best. But the part where like and there are some asymptotics, what happens past that, there's some bounds, what happens past that area. We recently had something that looks at a similar question for not making a graph bipartite, but making a graph Bipartite, things like that. A triangle free graph bipartite, you could make a K4 free graph tripartite and stuff like that. So we recently have something like that. We just had a paper accepted at like CPC or so yesterday, talking about this. But it's coming from that problem, just looking at it differently or expanding on it. But that was we tried the triangle, couldn't do it, and then we had some ideas and said like, yeah, well, maybe we can do something with our bipartite graphs, and there we found something interesting. It's like one of these things where you work on a famous problem and then you discover another interesting problem where you can actually do something.
Okay, good. Thanks.
Yeah.
Any more questions? I have another question, actually. Maybe a silly one. So is there like a general theorem that says that if I have some kind of extremal question, maximize the density of something subject to some other conditions, then I can get arbitrarily close to the correct answer if I consider flags on sufficiently many vertices?
There's something like that, right? Like this goes through like the graph limit stuff with Lovász and Schreiber and whatever. Like it goes in that direction. So
it's like if I had counterexamples with arbitrarily, for arbitrarily large flag algebra calculation, then they take like a limit and that will be a counterexample.
Yeah, you could probably do something with a graph limit language or something like that. Of course, this is of course silly if you want to do anything with a computer,
right?
Because you're very limited there. But there's other parts of Razborov's flag algebra method that does not rely on this plain flag algebra method where you do computations on small subgraphs, but you actually use things like derivatives and like talk about extremal things that you know because your extremal graph is extremal. About like things like a maximum has derivative 0. You can do something like that in the flag algebra language, and that's what Razborov himself did, and then Nikiforov did, and then Raya did when they talked about clique densities. They used that part of the method, which has nothing to do with computers. But that's not our specialty, so we haven't worked on that. But yeah, so there's okay.
Okay. Any more questions? I guess I have one more quick one. So I just so you said that with graphs you can compute pretty well, and with tournaments as well because there's the same thing. So presumably something like hypergraphs make things much worse in terms of computation.
Yeah, well, like that's like one of the driving problems that Razborov had was the K4 two-run problem on 3 uniform hypergraphs. That was like one of his motivation to even develop this method. And yes, the best known bounds are done with exactly this plain flag algebra method for this, but it couldn't push it all the way through. And yes, and we have done some stuff on hypergraphs and tried to find some extremal examples with iterative constructions and stuff like that. And it always looked promising, but we just couldn't push it through. In the end, like the bounds weren't good enough to make our stability arguments work or anything like that. So yes, you can compute on 3 uniform hypergraphs, you can compute on 4 uniform hypergraphs, but like on 4 uniform hypergraphs, you cannot compute on much more than 5 vertices or something like that. So at that point, it becomes fairly silly. So 3 uniform hypergraphs is still okay for very easy questions. But yeah, same thing, right? We computed on multicolored edges and stuff like that. We computed on like 4 different colors of edges, or sometimes you may color your vertices and compute on that. And that's something we actually did in this last tournament thing. We color vertices. So we can get local information because we color the vertices of a graph responding to the in and out neighbors of a specific vertex with 2 colors and just look at that. And then in this model, we can say something about that. Bringing sort of getting some local information, and that's how we find these cuts, and we can show these cuts. We could show that in the extremal example for this tournament, the degrees of all the vertices are in very, very small intervals. They only live in those. In the extremal, it does, right? And we can actually prove that like we can prove fairly strong bounds on where they live, and that helps us further to prove that the cut that we want is actually there, because we can sort of look at an edge or something like that, and then have 4 colors and say something about we count the edges that go this way and the edges that go that way, and therefore we cannot have the wrong one, right? Like we take a vertex of high degree, a vertex of low degree, and we show that the edge always goes from the high to the low degree vertex, and that gives us our cut into the high degree vertices and the low degree vertices. That's sort of the ballpark what we're doing there. Like I know it's very, very hand wavy what I'm doing right now, but I could probably talk a whole 40 minutes about that. And that's brand new. That's like what we did like last month.
Thank you. If there are no more questions, then let us thank the speaker again.
Thanks all for showing up. And
thanks for the wonderful talk. And our next week's speaker will be Matthew Kwan from Stanford.
Oh, cool. I should come by. Same time, same place?
Yep.
Okay, great.